first learning about substitution, we were thinking about, well, what happens when we start with the chain rule? How do we undo the chain rule? Right? That's what the whole point of substitution was, just to kind of remind you of that. And I want to remind you of that because the next topic is undoing the product rule. Right? So that's integration by parts. Just read online somewhere where someone was trying to claim that this is the most important thing that they learn in the semester. I don't know if I would fully agree with that, but it's valuable. And if you're going to take Calc 2, usually this is one of the overlaps. So depending on what happens in a semester, who's teaching it, what the topic is, some people may or may not get to integration by parts. And so Calc 2 usually starts by reviewing integration by parts. So if you're going to take Calc 2, you'll start with a review of this. Just kind of know that. Does anyone plan on doing that next semester? I think it's a good idea to kind of do it right away if you're planning on doing it personally. But anyway, let's talk about that. So I just, as a precursor here, this is the product rule, right? When you take the derivative of two things being multiplied, you do f prime g plus fg prime, right? We've seen the product rule a whole bunch of times throughout the differentiation section. And so now what we're thinking about is, okay, well, what if we integrate both sides of this? We want to undo the product rule. That leads to this, right? If you integrate that next row, it would look like what I just wrote down, right? So we're now have an integral on both sides. And if we integrate the derivative, we just get the normal function back. And so on the left-hand side, this piece right here, you're just integrating a derivative, and so the derivative sign just goes away, right? And so we just get f of x times g of x. On the left-hand side, excuse me, and then on the right, we can break that integral up into the two separate integrals. Right? If you have two things being added inside an integral, you can just kind of think about them separately, is what we're saying here. And so integration by parts, sort of, you can see, is starting with the product rule, but then we're going to rearrange it. We're kind of thinking about rearranging it into what's going to end up being this new kind of final method that we're going to learn. And so I'm going to take this piece right here on the middle piece there and subtract it over to the left side. And so that would be this, right? I don't know why I dropped my x's. Let me put the x's back in here just in case that's confusing. And if we just take this expression and switch the order in which it's written, we would obtain what's written down right below here. So from here to here, if we just switch the order, right? In other words, what I'm trying to say is this thing is just now written over here. You just kind of flip it around. And this is what we think of as integration by parts. So let me make that quick note. This is integration by parts. And this thing down at the bottom, the u dv v du thing, that's shorthand for the thing above it. And I think once we do a couple examples, this shorthand will make more sense. But notice how like it corresponds to the thing right above it, right? So we kind of think of u as being the f function, right? We think of dv as being g prime. So u, I think maybe the important thing to note is the middle one. We think of u as f and g as v. And so then du is the derivative of u, which would be f prime. So that's sort of the way to think about that. Anyway, we'll look at some examples and see how this works. But the takeaway that I'm trying to show you in this particular page is how we start with the product rule at the top. We're just rearranging what the product rule says. And then the idea is if you're given something in this kind of form, if you're given something that looks like fg prime inside an integral, we can use this formula. And so let me just make that note. So if given an integral of the form integral of fg prime, we can use integration by parts. Oftentimes people get really freaked out by integration by parts. I think it's partly a notation thing, right? That like is that thing I boxed in there is really ugly looking, and it's just a bunch of shorthand confusion, which is one of the reasons I like to try to cover it in Calc 1 as much as possible, so that if you do Calc 2, it's like a refresher or something that looks at least looks familiar instead of something that scares the crap out of you immediately in Calc 2. But I just know that it's the kind of thing that once you do a couple problems, similar to anything else in math, once you kind of see the way the notation sort of forms into an actual problem, makes you feel much better about it, and you can see the uses of it, right? It's one of the more useful integration techniques, which is why I think I read earlier today that's the most important thing someone learns in calculus or something. Anyway, so this is just the notation part so far. We're setting it up. The thing that we're going to use over and over and over again in this context, I'm just going to box it in again, maybe in a more careful way, is that thing that's now green. Right? The thing inside there tells us what integration by parts is. So before I sort of go into the actual process and do an example, are there questions about the notation or anything? There's not, I wouldn't expect anyone wants to hear anything too much, but this is a notation thing. Can I clarify anything about that?
So it's just pretty much moving f prime g to the left. That's why it becomes negative, and then you set it equal to the right part of the product.
Yes, yeah, that's exactly right. So we started with this product rule up top here, this thing, and then threw an integral sign on it, and like you said, rearranged it. So subtracted a piece over to one side, and maybe that's kind of a strange thing to think about. Like maybe you don't think about this as being something you can move around, but it's just some expression that can be subtracted. So yeah, we can have something like this, for example, and be positive, and then subtract it over to the other side and have it be negative over on the other side. Yep, that's exactly right. Other thoughts or clarifications and things like that? All right, let's talk about how to actually use it. This is the thing that you actually probably want to know, and the thing that'll be important moving forward, right? How do we actually use integration by parts? Well, as I just mentioned, you're going to be given something that looks like this. So it's going to be some function multiplied by some derivative. You're not going to really be able to tell necessarily which is the function and which is the derivative. And so here's how we actually choose which is which, right? So we need to choose one of those things to be u, and we need to choose one of them to be dv. And you can see if we look at the kind of, let me zoom in on the box here, whatever we choose to be u, over on the other side, we're going to differentiate it, right? And whatever we choose to be dv, over on the right side, we're going to integrate it. And so that helps us choose which is which. And it says that right here, right? So it says we're going to differentiate u, and so we want to make sure that whatever we choose for u, when you differentiate it, it makes it less nasty, or nicer is some way that I like to think about that. I know that's not a math term, obviously. You do something to make it less nasty. But when you differentiate polynomials, for example, the powers go down, right? And so they get nicer. So if you have a polynomial, for example, u is a good choice for the polynomial. As far as dv, let me do another color for that. The thing we choose for dv is just going to be whatever's left, right? So u is the important choice. dv is going to be defaulted to whatever's left. Okay, and again, the thing we choose for u, it means when we take the derivative, we want it to be like get simpler. right? So like e to the x, for example, doesn't change when we take the derivative. So that's usually not a good choice for you. Same thing with trig functions, right? They just become other trig functions. So that's not a good choice for you. Okay, and if that's still not clear enough, I actually stumbled upon this acronym long after I took calculus about how to figure out what u is, right? So if you just want like a method to figure it out, this acronym right here, ILATE, is a good thing to choose, a good sort of method to choose what u is. And so you just go through ILATE one at a time and think, do I have this? Do I have this? And if whatever you say yes, that's what you let u be. So I stands for inverse, L stands for logarithms, A stands for algebraic. What we mean by algebraic is polynomials. T stands for trig functions, and E stands for exponentials. And so when we choose u, we just kind of say, do I have an inverse? Yes or no. If the answer is no, go on to the next one. You just keep saying no until you say yes, and that's u. I know there's a little bit of writing there, so let me just pause and let people catch up. Let's see if I can clarify something there before we look at an example. Well, I'll finish the method, and then we'll look at an example. Thoughts about that acronym or what I'm trying to say in terms of picking u? You'll see it play out in just a second here, but okay, so once we have u picked, dv just ends up being whatever's left, right? And so then we differentiate u to get du. We integrate dv, to get v, and then we just plug them into the formula, right? uv equals the integral of v du, right? We just rewrite this in the new form with all the different pieces that we've calculated along the way. And then you'll see that the right-hand side of this, right, we're going to end up with something that looks like this. And so u and v are just going to be two things multiplied, and there's no instructions there. But the second half, the integral of v du or duv, is something you actually need to do, right? And so that's the last step. The last step is to evaluate the last integral and simplify. And something to note is that sometimes you need to do integration by parts again on that piece. So I'll just sort of say, may require more work. Hate to say it, but sometimes you got to do integration by parts twice. Or maybe it's really fun. I don't know. Maybe you can pretend it's fun or something. Does that ever work? Yeah, super fun. Tyson's into it. That can be fun. I mean, gosh, man, I wouldn't have studied math this long if I didn't get some enjoyment out of it, or at least think it's useful or something. So it can be. Throw that out there. Right? Isn't it kind of fun sometimes where it's like something's really hard and you just kind of get it? That's fun. I don't know, is that fun? Maybe it feels good. I don't know. Anyway, let's do an example. Can I answer a question before we look at an example? All right, so as I just mentioned, choosing u is the big important part here, right? So on this first example, let me write down this acronym, I-L-A-T-E. We want to let u be whichever thing we have in there first. And we're looking at this example, and I see an e to the x and an x. And so is there an inverse? No. Is there a logarithm? No. Is there an algebraic? Yeah, so algebra, as I mentioned before, usually means polynomial. And so that's the thing that we're going to choose for u. And so we're going to let u equal the algebraic thing in here, which is x. How's that look? Right? It's definitely not the exponential, because the exponential is the e, and that's way on the end. So we got to algebraic first. I guess I should also mention, I should have always started here. I take this for granted sometimes. I apologize. We don't have a rule to solve this problem, right? E to the x times x is not one of the rules we have, and its substitution isn't going to work either. right? If I let u equal x, du equals 1. That's not helpful. If I let u equal e to the x, du is e to the x. That's also not helpful. So substitution doesn't work. It's not one of the rules we have. We need a different method. Sorry, I should have started there. That's why we're using integration by parts. And is it also clear that u should be x? It's okay. Okay, so we pick u, and as I mentioned up here, dv is just whatever is left. And so if u is x, that automatically implies that dv is e to the x. Okay? And now we're on the bullet point that's right at the top of the page here. We're going to differentiate u and integrate dv. And so from here to here, we'll differentiate. And so du equals 1. And then we integrate dv. Right, remember d means derivative. So if we want v, we want to integrate. And in this case, it just stays the same. And now we have all the components of the thing I'm about to circle here in green, right? We have all the things inside that box. We have u, we have dv, we have v, we have du. And we can plug it in, and you'll see we get something that we can actually work with. So let me switch colors here. So what we found was the integral of u dv equals uv minus the integral of v du. I'm just copying down what was on that last page so I can scroll down. And we have all those things labeled right on the page right there, right? And so this becomes integral of x e to the x, that's what we started with, equals uv, so x e to the x, minus the integral of v e to the x du, which is 1. And that's easy, right? X e to the x on the right, this thing right here on the right side, we're just done with that. We don't have to do anything there. There's no instructions. It's just x e to the x. The second piece, we need to integrate this. But we can do that because it's just e to the x now. And that's an easy thing to do. And so that's how we would finish this one off. Right? We would do this integral. Evaluate that. That's a dx situation, by the way. And so that's pretty easy, right? That just becomes x e to the x minus e to the x. And what do we throw on the end after we finish off an indefinite integral?
Plus c.
Plus c.
Plus c. Thoughts? What do you think? And notice this. You can always double check these things, right? If you differentiate this, you can get back to the original. So if we did d over dx of this thing, we end up with a product rule in there. The first thing's a product rule, but it's like an easy product rule. The c goes away, right? Notice what happens here. We'd get f prime g plus f g prime. That stays the same. The c goes away. And look at this. These two things cancel. And we get right back to the original. So you can always double check those things, right? What do you think?
So that part that we evaluated before to get the answer, are you taking is that taking the antiderivatives of each number?
The thing that I'm circling right now, this?
Yeah.
Yeah, you're doing the antiderivative there, right? It's an indefinite integral because it's got the integral sign dx. And so, but what's the antiderivative of e to the x?
E to the f.
Yeah, it just stays the same. So that's why it kind of looks like we didn't do anything because it just stayed the same.
But then wouldn't you have to take
That's
the
what the antiderivative is. Sorry, go ahead.
I was just gonna say, then wouldn't you have to take the antiderivative of 1?
No. So, anything's multiplied by 1. The 1 part just came from the du. I was just trying to be clear that, right, this du ended up being 1. And so e to the x times 1 is just e to the x. Right, so I just wrote the 1 there just to be clear that we didn't forget about du. Du was just the number 1.
Okay.
Yeah, thanks for that clarification. Other things like that? All right, let's do one more. And I don't know. I was going to say, you could probably do this one, but maybe we should just do it together a little bit. But help me walk through it, right? So let's do ILATE again. Do I have any inverses, logs, algebraic, etc.? Not most of the time, but a lot of times ends up being algebraic, honestly. So there's no inverses, right? There's no logs. We do have algebraic again. And that's just a polynomial. And so we're going to let u be the 2t. And that means that du is just whatever's left. I mean, dv, excuse me. And I think that the notation is critically important here. If you understand the notation, then the next step is obvious. If you have u and you want du, you
then you find
differentiate.
then it'd be 2.
Right, 2. Excellent. And if you have dv and you want v, you integrate. Right, and so what's that? So du, like I think that was Janetta just said.
So
2.
then v would be cosine.
Cosine.
Negative cosine.
Yeah, minus
Negative,
cosine.
my
I always
fault.
have to double check that myself. Minus cosine. But then, this is the hard part, so to speak, because then once you have all these different components, it's literally just a matter of putting it into that formula. And then the integral that you need to do should be an easy one because you should have sort of gotten rid of the hard part. Unless you need to do it a second time, which we'll see. We won't see that today. We'll see that next time. And we just sort of stop here and see if this looks okay before we write down the answer. All right, let me copy the method again. So it was the integral of u dv equals uv minus the integral v du. Right, I'm just copying down what it says right at the top of the page there, and we have all these components, and so I just like to write that down so you can see how they all fit in. All right, so our u in this case was 2t, our dv was sine. And then when we integrated and differentiated, we ended up with the following, right? So u is still 2t, but now v is minus cosine. And then v du would be minus cosine times 2. And that integral on the right's not too bad, right? Let's simplify it a little bit so it doesn't look so bad, but That's a minus 2t cosine t. And then the two minuses there cancel into a plus, and we'll have plus 2 integral cosine. That's pretty easy, right? See if that looks okay. So we get a plus in the middle because you have a double negative that cancel there. And cosine just becomes sine. So we're right at the end here, right? We just do the integration, and that's it.
So at the end, we do integration.
So you're just following the instructions, right? So this tells you right here to integrate. Right, when you've got something sandwiched between the integrand, which is the s thing, dt, that means do the integral. Yep. And also that's where the plus c comes from, right? Because it's an indefinite integral, and so you get the plus c from that piece.
Okay.
And you can double check this, right? If you take the derivative of this, you should get back to the original. So that's good practice, like for the final, for example. I could definitely ask you to take the derivative of this final piece on the final, just for example, right? You'd get a product rule. This would end up being a product rule if you did that, and then stuff will cancel and you'll get back to the original. Ooh, ow.
Hey, Professor, what's an inverse?
Yeah, so that's a good question. Thoughts about inverse? What do people think an inverse is?
Yeah.
So it means like something to the -1. So like that would be an inverse thing. Just like 1 over.
And if you see that, that takes priority. That becomes you.
That takes priority. Yep.
Okay.
Yeah, I'm just doing a quick search here just to make sure I'm not missing some other particular type of inverse. Talk specifically about inverse trig functions potentially. So I'd say that one doesn't come up a lot. Let's add a note to that up by the I late part, the original part. And so when I'm seeing, just on these couple examples, I'll just Google quick. Usually is that the inverse means trig inverses. So things like cosine to the -1 or sine to the -1, tan to the -1, etc. We don't see though, we don't do a lot of trig in Calc 1, at least not in this version of Calc 1. I've mentioned this a couple times. Trig, in my opinion, comes up more so in Calc 2, but in these kinds of contexts, right? I mentioned that integration by parts is really a Calc 2 concept, and so you start to really build in some of the trig stuff in Calc 2. Yeah, so inverses, I believe, are trig inverses specifically. So if we look on this, no bounds, that's why we get the, wherever it is, we get a plus C somewhere, right? You end up with a plus C in your answer because there's no bounds. Now I just want to sort of talk about, well, what happens if we have bounds? How do we actually get area from one of these integration by parts problems? And it's pretty straightforward. It's probably what you would imagine we would do, right? So the, this is just uv minus the integral of v du is just the formula for integration by parts. And now we're just taking the bounds that were here. Let me make this transparent again. We're taking the bounds that were here, and then we're just putting them here and here as well. But notice the notation, right? This has got the straight line with it, and this is the integral. And so let's just quickly talk about the difference between those two things. This part, when you write a straight line, that just means plug the points in, right? So if you have something that looks like that, function, straight line, integrands, that just means plug in the second one minus plug in the bottom one, right? And so the thing on the left, you just like plug the numbers into, in other words. The thing on the right, you got to do the integration. So that means 1, do the antiderivative, 2, then plug in the points. All right, so just hopefully that was clear, but I just want to be clear about that note. It's a notation thing again, right? It's instructions. It's just knowing what those instructions are telling you to do. And it's the same formula. I'll just make that, I said this in words, but I'll just note that this is the same formula we saw above. It just has bounds now. Thoughts about the notation or anything there? Because we're just going to revisit the problem we just looked at a second ago, this x e to the x1. Right, that was one that we just looked at from above. Except now it's got the number 1 and 6 with it, right? And so instead of just doing some random antiderivative, we're actually going to find the area of this thing. And so I'll just go ahead and write down the work we just did a second ago, but I'm going to fly through it because we just looked at this one moment ago. But maybe it's good to see it one more time in fast motion. So the I stands for inverse trig functions. We don't have any of those. L stands for logarithms, no logarithms. Algebraic expression, yes, there's the x. And so that's how we chose the u part. And then that means whatever's left is dv. Right, so kind of just zoom in over here. This ended up being our u. This ended up being our dv based on the acronym. And what we said was, to get du, you differentiate, right? Here to here, differentiate. If we want to get v, we integrate. And nice thing about e to the x, of course, is it doesn't change. And that's why it's never going to be u, by the way, right? Notice how exponential is like the last option. We'll never let exponential be a u because it doesn't change when you take the derivative. So it's not going to really improve anything. Okay, and then we just write down uv minus the integral v du, but now we have the bounds, right? So I'm just going to slide up here and just show you where I'm copying this from. I'm just going to copy this literal thing we had before, right? I'm going to copy that exact same thing, except now it's going to have the numbers 1 and 6 associated with it. So it looks like uv, but with the bounds, minus the integral of v du. Oops, I forgot to put the bounds on the second integral, right? It's from 1 to 6 now. And just like before, we integrate. You need to integrate this piece, which means find the antiderivative. And it doesn't change, but the difference here is now we don't do a plus c, right? Now we're plugging points in, right? It's a definite integral. And so we're going to do this. Right? E to the x stays the same, and it looks like this. Let me just pause there and let you kind of compare this to the thing from the thing right up top there. Thoughts about that at all? Can I clarify anything there? So then, both these things mean, both of these notations, 1 to 6 with the straight line, just means we're going to plug the points in. Right, and so that looks like this. first plug in 6, then plug in 1. First plug in 6, then plug in 1. And, you know, something kind of interesting thing happens here where the e's to the 1's cancel because you have a minus plus situation. And then you have 6e to the 6 minus 1e to the 6. So that's just 5e to the 6. And so you're welcome to leave it like that. This is a test or something. I would just leave it right like that. If you're curious, this is approximately 2017. Looked at that in a calculator earlier. Make that a little more legible. Just to be, you know, totally clear about what we did there. Where do I have some room? We can slide the graph of this in. The plot of this is actually kind of interesting because you'd think it'd be some strange thing because it's an exponential times x, but it's really just like, it's like a scalar multiple times e to the x. And so it makes e to the x look steeper is the way I think about it. So it looks like kind of like this. It's like a super steep version of e to the x. That's what x e to the x looks like. And we just found the area from 1 to 6. So we just calculated or estimated, sorry, not estimated, we found exactly the area between 1 and 6. Thoughts about that idea? All right, let's look at one more, and then I'm going to give you a chance to try one here. On this next one, we've got ln of x. Let's just draw the graph right up front, just to remind ourselves what we're trying to do here. So we know ln just looks like this. And so we're trying to calculate the area under the curve there from 5 to 10, which seems like it should be pretty easy to do, and it's not terrible, but it is an integration by parts problem, right? It feels like it should just be kind of easy, but it takes a little bit of effort. Because we don't actually have a specific rule for ln. I mean, we can certainly write one down and make one up or whatever, but we can use integration by parts to do it. Now, the tricky thing here is, and maybe you're already trying to think about it, is what do we let u be? And so I'm going to write down ilate again. But if we want u and dv, there's only one thing in there, ln, or is there? Right, so do you see the dilemma a little bit here? Any ideas? I'll give you a hint, but I'm just curious if anyone has an idea.
It would be like x, it's u, and then no.
Good thought. So usually, and not usually, with let me sort of, because I think what you're doing is thinking a little bit about the chain rule.
Yeah.
And substitution. And when in substitution, we always let u be, or not always, but a lot of the time it ends up being the inside thing. Now it's in integration by parts, it's like two things in there and you let u be one of them and dv is the other. So you can't really let it be something inside the other thing, in other words. But that's a good thought. That was a really good thought because we only have one thing. And so I like the idea of like, well, we don't really have one thing. We've got x and ln. So thinking about them separately, but just trying to think about, I'm just trying to say that that's not going to work here because we need it to be like two separate things. And so the sort of trick here that I would describe is ln is really like the number 1 times ln. And so if we think about it like that, there are two things in there and one of them is the number 1. And then if we have the number 1 written in there, then we can use ilate to actually get the correct thing. And there's no inverse logs, inverse trig function, excuse me. I don't know why I keep saying inverse logs. There's no inverse trig function, but there is a log, right? There's an ln. And so that ends up being the u. And then that means dv is the other thing, quote unquote, and the other thing is just the number 1. So I realize that's a little strange, which is why I'm kind of showing it to you. And, you know, newsflash, but upper level math has a lot of like tricks like this. It's like, ooh, do you know this little trick about how it's not just ln in there, it's ln times the number 1? Like, who would really think about that? Well, I think about that because I've seen little tricks like that a lot. So anyway, just sort of the more you see this stuff, the more it comes up over and over again. Anyway, questions about that idea? Because then, you know, once you pick u and then dv follows, you just follow the algorithm and you get the answer. Right, so du, as we differentiate that, that becomes 1 over x. That was the opposite of the question at the start of class, right? We integrated 1 over x to get ln. So we're doing the opposite there. So differentiated. And then we integrate to get v. And when we integrate the number 1, we get x, right? And so some interesting thing happens when we start to do uv minus the integral of v du. How much room do we have here? Let's sneak it in right here. So we're going to do uv minus integral v du. That ends up looking like this. ln x times x, which is not helpful, but you don't have to do anything with that, right? You don't have to integrate. Like, that's kind of an ugly thing is what I mean, but you're just going to plug numbers in there. And then v du ends up being x times 1 over x. And so those two things cancel out, right? Oh, let me throw the integrands on there too. I forgot that. So they're from 5 to 10. Thoughts? Seems okay. So the x and the 1 over x cancel into the number 1. Maybe I should just write that step down, right? It ends up being just integral from 5 to 10 of the number 1. And that's super easy. Right? It just becomes x, and then you plug the numbers in. So I'll write that step down too. Right, we just plug the numbers in at this point. And it ends up being this. Oops, except you plug in the top number first. ln 10 times 10 minus ln 5 times 5 minus 10 minus 5. Did not get an approximate answer for that ahead of time. Not super concerned about it. I mean, you know, if this is a test and a couple people just left it like this on the test, totally fine with me. You know, how well you can plug things into a calculator is not super important. Can I clarify anything there? I would describe that one again as kind of like a trick sort of one, but now that you've seen that trick, maybe you'll see one with an ln in the homework, right? And if you see one with an ln or something like this, maybe you'll have an idea of how it works. Can I clarify something?
Can you explain how you got in the integration? You got 1.
Yeah, so u du ended up being x times 1 over x. And so you have x over x, right? So the x divided by x just cancels into the number 1.
Oh, okay.
Yeah, this just turns into that. Another way to say it, right, when you have a number divided by itself, you get the number 1. Other thoughts? All right, this is your chance to see if it makes sense. So there's another example. It's got a trig function. We haven't done one with the trig function today. Do Did we do one last time with a trig function? We did, sine 2t. Oh, so we did this one previously. So it's your chance to give this one a try. Remind yourself how you did that one last time, except now it's got bounds on it, of course. And so, you know, I won't sort of like let you work on it for 5 minutes or whatever, but let's do it in stages kind of thing. Like I'll write down I late, take a second and think about what you should be. Which one of those things do we have? And then whatever u isn't is dv. Right, take a moment there and think about which of those things we have. And if you need to, you can scroll up or whatever, look at back at that last page, but try to do this one fresh. Thoughts? What do you think you should be? Anyone?
Wait, are we supposed to say what you should be?
Yeah, what do you think you should be?
It should be signed, shouldn't it?
So when we go through these
Well,
things,
actually, it shouldn't be signed because that's trig already. So, and trig should be one of the last ones.
yeah,
And algebra is supposed to be before trig. So 2t.
Nice job thinking through that one. Yeah, I mean, right. So that was a good point. Like trig is one of the last ones, and so very seldom is u going to be a trig function. Oftentimes, if there's a polynomial in there, it's a polynomial. But you know, these other things take precedent. We mentioned before, we're probably not going to see an inverse trig function in here, but we saw a log in the last one, so that happens sometimes. Anyway, so yeah, so u ends up being 2t. And that means dv is the other thing. Oops. Sine. All right, take a second and just think about what is du? How do we get du, right? What's dv, or v, excuse me. All right, how do we do that? It's just starting to come into focus in our mind. What do we do there? Trying to get you to walk through this, and then I'm going to sort of push you along, right? So u is just a function. Du means the derivative of that function. So that means we're going to differentiate. dv means we have a derivative. That means v is the antiderivative then, right? And so that's going to be integrate. Or antiderivative is maybe the other way to say that. All right, so when we differentiate, hopefully we all see we get the number 2. And when we integrate, sine turns into minus cosine. A couple of people I was looking at that today put plus cosine. And I know those are confusing. Don't get me wrong. I struggle with those as well. All right. So take a second and write down the next step, right? We're going to write down u v minus the integral of v du. Go ahead and do that yourself. And then when you pop your head up, maybe it will be the same thing I have. Maybe I'll just wait 1 second. And we're going to have bounds on these too. So maybe I'll throw the bounds on this thing, right? We're going to have from 0 to 10 in this case. Sorry, I just muted a couple of people. I was getting some feedback from, or some static from a couple of people. All right, so that uv ends up being, let's see, u is 2t, v is minus cosine from 0 to 10, and then v du minus cosine, let's see, times 2. How's that look? And I'll just simplify it before I do anything else because there's a bunch of minus signs in there, right? Maybe the minus sign's a little bit tricky because the first minus sign just makes this thing negative. Right, just like a minus 2t now. But then the middle 2 minus signs, these 2 things are going to cancel into a plus. And Another way to think about it is you're pulling a -1 out in front of the integral, and then you have a double negative there. You could hold off on that and if you want, because cosine will turn into sine, and you could deal with it later. But I'm just seeing that right now, and so I just thought I would throw it down there. Oh, and then the 2 comes out front as well. And so that's really the kind of thing we want to be thinking about for this one. Look right. You know, these kind of simplification steps are important because if you look at that first thing in blue, it can get a little bit daunting because there's all these negative signs and what's going on. So maybe before we do too much, we can just kind of simplify it a little bit and make it look a little bit easier. Look okay? All right, I'm going to do the integration and plug the points in. So I'm going to still just leave this alone for right now. We could plug them in whenever, but I like doing it all at once. So let's see. Cosine turns into sine from 0 to 10. Wait a second. Derivative of sine is cosine. Cosine is sine. Yeah. And we plug the points in. And it would look like this. -2, I'll do it. -20 cosine 10 minus 0 cosine 0, if you will. And then the other one is 2 sine 10 minus 2 sine 0, which is also 0. That one's not actually that bad. Cosine 10, we might, sine 10, we'll need a calculator for. I'm just going to leave it like that. Looks like we've got some activity outside here, huh? Sounds like it. How's it look? Integration by parts, love it, hate it. It's not that bad.
Yeah, I like it better than some of the other ones like substitution.
Great. Yeah, a lot of people, for some reason, like substitution better. Now that I'm re-looking at integration by parts for the first time in a little while, it does seem a little bit more straightforward. It's just like, make sure you pick U right, and then everything else should kind of follow. You know, I say that, and then we're about to look at one that's a little bit tricky, so they can get tricky. Thoughts, though? Other thoughts? Okay. So the last one here just sort of points out that, hey, sometimes you actually need to do integration by parts twice, unfortunately. This is where maybe John will get off the wagon of integration by parts. That's where it can be kind of tedious, to say the least. And because, well, let me actually point out the last one. The reason the last one works so well, and a lot of the previous ones, is because the thing that you let U equal was linear, right, is a power of 1, so that when you took the derivative, there was no variables left. And that was helpful because then when you put it back into the integrand, it was just a constant. And so if it was a bigger power, we'd end up with a t in there, and then we'd be kind of in the same situation we were a second ago. And so that's what happens on this next one. What is it? Can you guys hear me okay? There's like someone mowing right outside my window right now. When we take the derivative of this, that's going to end up being u. It's still going to end up having an x in it. And so we'll have to do integration by parts twice. Is it the end of the world? No. Is it kind of ugly and long? Yes. So I think everyone can follow this. At least I'm not getting a lot of questions. So it seems like maybe folks are sort of getting this so far, but you'll see what happens here. I think about the I late. It's going to be a again. And the a is the quadratic. Right, so our u in this case is this thing. And it's not going to go away, quote unquote, when we take the derivative. Right, and so dv is cosine. You know if that's not okay, but Is that right? So the predicament here is that when we do the du, when we differentiate this, we still have x's. This thing is going to be a problem, the x, because when we stick it back in, we're going to still have trig function times x, and so we'll have to do it a second time. Just kind of looking ahead at what's going to happen. Right, and then we integrate the second part, of course, and we get sine. Right, so when we do uv minus integral v du, here's what it looks like, and you'll see that there's an issue here. So let's see here, uv minus integral v du. And the spot that we're in right now looks very, very similar to the spot we started in. Right? It was like trig function times polynomial. It's just slightly better because at least it's not a quadratic, right? It's not a power of 2, it's just a power of 1. And so we can imagine when we do integration by parts again, on that piece, the linear function is going to go away, or it's going to become a constant at least, and then it'll work the second time. So that's the sort of thing that I am talking about.
So I kind of see that, but like when you originally have 2x squared plus 3x, why won't that like work?
Because when we differentiated it here, let me do another color so it stands out. When we differentiated it here, it still had an x in it, and so when we ended up sticking it in, it still had an x. Or I think the better thing to do is to compare it to the last one, or some of the previous ones. Like in this case, when we differentiate it, we just get a constant, and so then when we stick it back in, it's nice, right? It's just a constant multiple. Same thing with like this one, right? When we differentiate it, we just got a constant, and so when we stuck it back in, it was just a constant multiple. So if it's not just a linear function, i.e. power of 1, like this one was a linear function too, which made it nice, then we're going to have to do it twice. Or maybe another question is, what if this was like 2x to the 4th, ... How would that change things? John or anyone else?
You have to do it like more than twice, like 3-4 times, or I don't know.
Yeah, we'd probably, so, you know, this one meant we did it 2 times. This means we'd probably have to do it 4 times. Would you expect to see a problem like that? I hope not. I mean, you know, not on like a homework or something, but just practically speaking, that's what it looks like. And every time, and you'll see it in a second, every time we get another integration by parts. So it's like, it just gets bigger and bigger and bigger. It's kind of like, you know, we're undoing the product rule here, right? So remember when we did product rules inside product rules, and we had like 1 became 2, and then if you had a product rule in there, it became 4, and then if you had another one, it became 8, and it just kept being crazy. Anyway, other thoughts?
Wait, so basically you're going to have to just do it again inside of the problem or something?
Yeah, because right, the next step here is to do this integral, and if we want to do that integral, it happens to be an integration by parts question, and so we did integration by parts, but now we're looking at this and we're like, oh, we're still in that same situation, and we're just going to do it a second time. And it's very similar, right? Because u is the 4x plus 3, and so that means du is just 4. So that's going to be good because that's just going to be a constant multiple. And then that means dv is the other thing, which is sine. And so v is minus cosine. I think that's right. And so you can see I've left some room here because I knew this one was going to be kind of long. So this part just kind of copies down, right? This part here is just going to, we didn't change anything there. But the next piece becomes the integration by parts. So it's going to be like u v minus integral v du. And, you know, again, this is a definite integral. And so if it was an, sorry, it's an indefinite integral. If it was a definite integral with bounds, it would be even crazier because then we have to plug stuff into each one of these things. Excuse me. All right, just going to pause there. I think I'm going to end with this one too. So I'm going to kind of slowly do this, see if anyone has any questions here. And so I guess the point here is notice how this thing that we ended up with here, cosine 4x, or sorry, cosine x times 4, that's a super easy thing to do, right? It's a constant multiple times the integral. I'll simplify it just to kind of show you that, but writing the next line now. Okay, I'm going to just, yeah, this is where it gets a little confusing. I'm going to distribute this negative sign. So it's going to make this thing positive, and then it's going to make this thing negative. So it's going to look like this. Let me know if this looks okay.
You were able to do that because there's like a hypothetical one there. Is that
The second, so yeah, this is where algebra, you know, like having an understanding or a strong understanding of algebra can be really helpful. So it's like this negative sign was subtracting this whole thing. And so that's the same negative sign. It's just that the inside piece became a different, bigger thing, but the whole thing is still being subtracted. Right, so like when I did the integral, it's like, okay, but this whole thing still being, that's why I was trying to be careful with this, like doing the brackets.
all right? That's clear.
And then, you know, just to make it more clear for other people who are not a little confused, it's like you had a negative here and a negative here. So that's why it became positive. And then the third one, it's like you have 3 negatives. You have these 2 negatives, which make it a plus. But then this one makes it negative again. That's why this one is negative. It's like -1 times -1 times -1. So that's a bunch of algebra, mostly, not mostly, that is just algebra. Let me know if it's confusing. I'm happy to clarify it. But, you know, if this is a test, I wouldn't do something that's, I hope I wouldn't do something that confusing. All right, then we just integrate that last part and we're done. We got to throw the plus c on though. Don't forget about the plus c. We did all this work. We want to have the plus c. See, so cosine turns into sine plus c. Whew, that one's a little bit of a doozy, but if you can follow that, kind of understand why we need to do it twice, I think you're in great shape.